So now let's look at the first of those geometries where the plates are spreading apart from one another at a divergent boundary. Looked in your readings, and so the Johnson text, I did find the divergent boundaries in section 2.4. There's a link for those. And then the Lumen text, it's within module 5, and I believe most of it is going to be in the part that says readings, theory of plate tectonics. But again, I am not as sure about driving the Lumen text. So I'm open to anybody that does know better how to reference stuff in that. I can't tell you a page number or anything because there aren't any. So y'all tell me where y'all are finding it if you find it somewhere different. So diverging plate boundaries. Divergent boundaries are the first of our three types, and it is, my arrows seem to have gotten a little confused there, but the orange down here is the divergent, where they are pulling apart. So lots more detail here about the pulling apart and the motion and the movement of those plates, right? And I understand that there's a lot going on these slides, and we're going to focus on these green vectors right here. All this other stuff is loading rates and extensional rates. The original paper here in ResearchGate, and if you don't know about ResearchGate, give me a message later or an email to talk to you about that. It's kind of, ResearchGate has been called Facebook for scientists. So a lot of folks publish their research there after they've put it into journals, because journals like to charge people for access, and ResearchGate is a way around that, because the researcher can a lot of times post their own stuff, whether the journal wants to charge you for it or not. They can post it for free, and scientists often want to get their stuff out there for free. They don't want to set up paywalls and charge people. They want the science out there. So ResearchGate's good for that. Okay, let's talk about these green vector arrows here, and we're going to talk about movement of these plates. And for this one, I'm going to focus here on the Pacific plate and the Nazca plate right here, and look at the fact that the Nazca plate is going east, while the Pacific plate is moving away west, or really west-northwest, but basically apart from each other. And so this zone right here is where they're pulling apart and leaving a gap, you can think of it as. And you can look at these motions in the context of all the other plates around them, so that the Pacific plate moving west, and you can see how that westward movement, we're going to get to eventually what's happening over here on this end. Something's got to give over here, right? But that movement that direction, and then the Nazca plate moving east the other direction. So they're pulling apart right there in the middle. So zoomed in on that previous image right here, that's those same two vector arrows that you were looking at before, and that's kind of what's going on underneath as that Nazca plate is pulling away this way, and as that Pacific plate is pulling away that way. They're leaving this tensional area, which is gapping open, rifting, and allowing material here to start to melt and make its way up to the surface. I think for this course, it's okay to think of this as just molten material down here. I mean, it's not really. It is a solid phase, a ductile solid phase, and then when the pressure is released from that rifting, you get melting going on of it. It requires it to already be very hot down there. And then, of course, we can explain that rifting again. Your old friend, the phase diagram. You just keep seeing this over and over again. So let's say we have a material right here. This is our condition. So it's at a certain high, that's a high pressure, like under like tons and tons of rock, which it is, right? So you have it there, and you have a pretty high temperature. Here we're talking about 1700 C. All right, so we're going to start from right there. Now, you're familiar with the idea if you have a material at a certain pressure and you increase the temperature. So increasing the temperature is moving vertically on this diagram because the temperature scale is on the horizontal, on the vertical y-axis here. So if I increase the temperature, I'm going to move vertically on my axis, and that tends to melt the material, right? So you're moving from this solid phase right here into this whole zone up here. See how it's labeled liquid right there? So you're moving from a solid phase across that boundary line, and that's the melting line. And so it melts into a liquid. In this case, this is ilmenite and perovskite. So this is a magnesium silicate melt. So you have a magnesium silicate solid here, a mineral phase, and it melts into a magma right there. Okay, so that's moving temperature. But now let's go back to our starting point. So we had that 1700 C and 13 gigapascals of pressure. So the exact same idea with increasing temperature. If you decrease pressure, we're going to move on the horizontal axis this way. And the same thing can happen. We can melt it just as easily that way. So as you decrease the pressure, you cross this boundary line. And so you move from the solid phase, actually through another solid phase here, but you move from the solid phase through that into the liquid phase. And moving into the liquid phase gets you to melt regardless of which direction you were going on this phase diagram to get there. A couple of additional notes from that previous screen, and if I go back it'll reset my recording, so I'm putting them here on the beginning of this slide. One is that we'll get more to that, and if you look back to those melting diagrams later, when we get to the igneous rocks section and we talk about Bowen's reaction series, you'll see that it's actually only a partial melt going on there, and some of the minerals are melting out, not all of them. Okay, so another thing to note from that is if I were taking this course and I saw this phase diagram thing pop up this many times in lecture, I think I would start to think about studying that hard for the midterm. Okay, so moving on to, well, I dug into those textbooks that you guys chose, and the Johnson text has some pretty interesting stuff about rifting. And so rifting is a part of the divergent boundary process, and I want you to, if you're watching the YouTube video of this, I want you to pause and go to the links for this, or if you're already in the Johnson text, it's section 2.4. I've also put a link on this slide, and you can get to it right here. You could also go into the textbook links in the content area and get to the Johnson text and find section 2.4 that way if you would like. There are a couple of really good animations that you should watch in there that give you a good walkthrough of that. And then come back and continue this after. We'll talk about some of the details in that Johnson text. So if you went to the Johnson text and read there, you'll see this graphic about the Horst and Graben system, and this is a good detail of what's going on there. So over here you have the extensional system, and over here you have the extensional system. So those two blocks are pulling apart. Now think of the idea of just gravity working. So you've got these blocks here in the middle that are supported, and as the tension pulls apart, then their support is going away, so they're likely to just slide down, to fall. And so gravity is running this system right here and creating these blocks that drop down, and you have these valleys forming in between the Horsts. So the Grabens are the valleys and the Horsts are sticking up in between. Also, I would note, particularly for Laura, you're talking about the archaeology stuff and the Rift Valley in Africa. There's a good picture of it in that Johnson text, by the way. The Rift Valley, where we find a lot of the early hominid species, we're finding them in these rift valleys. It may be kind of, I know there are some competing theories about where the cradle of the species is, but these Rift Valley valleys and the Horst and Graben system may be some of that in Africa. So let's look at that over time. So what you get, so think about the Rift Valley as it's happening, right? You're just starting to break open that Rift Valley there in Africa. Let's look a little further east from where the rifting is happening right now in the Rift Valley on the land, out in the Red Sea. And sort of you have the same thing happening there. Early on, it started to break up like this and spread. And you get a developing, spreading center like that. And then as it develops a little further, it starts to drop down, like we were talking about with the Horsts and Grabens. You get this major drop area, and you get this developing zone. And think of this, I kind of think of it like the Red Sea right now, where it's starting to open up. We get some volcanics in the middle of the Red Sea, and you've got this opening seaway right there. And the same thing you can think of happening when North America was splitting apart from from Asia and Africa, what became Asia and Africa and Europe eventually. But when it's first starting to break up there, you got that original Rift Valley type thing that developed into this shallow sea zone, kind of like the Red Sea is now. And then eventually it spreads to a wide ocean open with a ridge system, a mid-ocean ridge system in the middle, and this wide plain that we talked about, the ocean abyssals are here, and you get all of this developing. So if we were around long enough as a species, we could see the Red Sea eventually develop into a wide ocean like the Atlantic has done, assuming that the continental drift remains the same vectors that it currently is. And there's going to be a problem with that in the way Africa is currently rotating into Europe. But a simplified system, you could get the Red Sea developing into an ocean like the Atlantic. So this is a major part of what Wagner was missing. So you get, if you had, Mr. Wagner, if you had this Pangea thing, how could we move this stuff? How could we break it all up? Why aren't there boiling magma seas here where you think it broke up? Well, the spreading centers, the basalt flows in between, that's the answer to that he didn't have at the time. And so you get Pangea here breaking up a little bit, and then a little bit more over. So that's Permian. This is Triassic. So this here is the beginning of the dinosaurs. Remember the stuff we talked about with the ages early on. So you want to look at your geologic age chart to know where I'm talking about there time-wise. So that's Triassic, 200 million years. And then you get in the Jurassic, which is middle of the dinosaur period, right? Middle of the Mesozoic. You get a little further spreading. We're still connected up here across the northern Appalachians into Scotland and Norway. We're still connected to Europe there. And then you still have South America and Africa connected here. These have broken apart some, but they're drifting further. Now, Cretaceous is kind of the pinnacle of the dinosaur period, right before they go extinct. You get up to 65 million years ago. And you can see the geography is developing a little more. South America has split away from Africa here. We've split more from Europe. This is India right here. It's sliding around by itself at that point. It's about to run up into Asia here. That impact is still going on. We'll talk about that in Convergent. And then eventually you get to the present day, and you have the continents as we see them now. So this is the stuff that Wagner was missing when he tried to explain his intuition about the Pangea idea.